Okay. Okay, see my screen?
Yes, Doctor.
Doctor.
Okay, so today we're going to continue with systems. Okay, last 2 weeks we had discussed on the signal. Okay, we have discussed on the signal. So signal. So you have the continuous time signal, and then you have the discrete time signal, and then you see we discuss on the periodic or non-periodic, and then standard form of signals, and then what else? Even and odd signals. What is even and odd signals? And then multiple transformation that we can do on the signal, both signal, continuous time signal, discrete time signal, and then energy and power signal. Okay, so this example. Okay, so we discuss a lot more. Okay, so you have this continuous time signal and discrete time signal. So signal. So the signal is information where you present it as normally we present it as amplitude versus or varies with time. Okay, so the amplitude. So the amplitude so could be voltage, it could be current, chemical concentration, oxygen concentration, anything that that convey or provide us information. So that varies with time. So that is signal. So also signal you can see it has a standard form. Okay, the shape. So when it varies with time, so we can put a special name on it. Okay. Other than this, we have sinusoidal signal. So we have in form of cosine, sine, exponentials. Okay. So that is signals. Okay. So we plot it. We plot it on graph. So the amplitude versus t time. Or for discrete, you have n. Okay, the amplitude versus m. Okay, the amplitude versus n. Okay. So we have seen that. Okay, so this week or today we're going to discuss on the systems, right? Systems. So you have a simple block diagram here. So we have this. So we have input signal and then we have output signal. So we want to discuss the systems, okay? Okay, so this is the whole system where it has input signal, this is output signal. All right, so this is output signal, this is input. Xt is the input, yt is the output.
Sorry.
All right, okay. So here, a system is anything that responds when stimulated or excited. So a system, anything that respond to the input, okay, process the input, okay, and then provide the output, okay. So what we have nowadays, or the system that you going to create, design, we call it as artificial systems, all right, okay. So we do also have natural system or biological systems. Okay, like our body, we have these respiratory systems. So the concentration of the oxygen or the level of oxygen is the what we call it the signal. Okay, and the system, the lung, the bronchus, the bronchial, the trachea, all that form the systems. Okay, So and then other biological system you can have our nervous systems. Okay, that is example for biological systems. Okay, we can have respiratory system, nervous systems. Okay, so you go and check. There are a lot more. Okay, on that. Okay, and then for artificial system, the one that we have discussed in the first week was the communication systems. Okay, you have that. Okay, that is designed and built by humans. That artificial systems like the nervous system, respiratory system is not designed or built by human. It's there already. Okay, so engineering system analysis is the application of mathematical method to the design and analysis. Okay, so here you know that system has input and outputs. Okay, so this is a simple system, right? So the block diagram here, simple block diagram. So xt, normally xt is input, input signal. So yt is output signal. Okay, but you can also have other than this. I mean, other than this, if you want to have this as ft, zt, should be okay, as long as the one that goes into the input here is input, the one that come out from the system here is output. Okay, so you know that. So anything that goes into the system is input, anything that come out from the system is output signal. Okay, so so this is the simple block diagram. Okay, the operator h, this one h is perform any imaginable operation. So any operation on the system. So we could have in here addition, okay, or signal integration, any process that happen in the system. So this operator H perform that, shows that operation in the systems. Okay. So this is a simple, or this is a more complex block diagram. So you can have more than one input signals. Okay, for example, here we label as x1 and x2. Okay, so h1, h2, h3, h4 is a subsystem. So the main system here is this, right? So this is the main system. So in the main system you have subsystem. So means we can also have this, okay, as a systems. Okay, not necessarily just one input, one output. So we can have more than one input and more than one output. Okay, or we can have one input, more than one output, or more than one input, more than one output, or more than one input, just one output. So that is system. So you can have, it depends on the design of the system. Okay, so this is a multi-input, multiple output system example. So you can have single input, multiple output. You can have multiple input, single output. Okay, so it depends on what you are going to have here. Okay, so this is block diagram to show relation between input and output with the systems. Okay, so before we go further, okay, so this is just to show you common symbol use. Okay, so this is also simple block diagram. Okay, so you have x means input like xt, and then k is the constant or amplified, so output be kx. Okay, so instead of using this square, you can have the triangle here, or also you can have this just arrow, put k, so you know the output will be kx. Okay, the output be kx. This is in your textbook, if you have Robert textbooks, they will use this. They will use this for amplifier, the last one. So the one in the square here. Okay, and then common symbol for summing junction. Okay, let's say you want to do addition between two signal, so you have signal xt here, so x or xt, and then you have yt here, so you have this, we call it summing junction. Okay, plus plus, so means that here you see this positive sign here means is positive x. Okay, so the negative here means y times negative become negative y, so the total when you do summation x minus y. Or the summing junction can also be drawn like this, using the summation symbol, sum. Okay, or just a circle without anything inside it. Okay, okay, so if you have let's say this one minus, so x, so this is the summing function. Okay, so look at the third summing junction here. So if let's say you have this negative here, okay, instead of positive you have negative there, right? You will have output negative x, negative y. Okay, okay, so again here lagging happen again. Okay, so again here, I repeat it again. So let's say if you have this is your summing junction. Okay, look at the second summing junction here. Okay, if this symbol plus symbol here you replace with negative, so means that your output be negative x, negative y. Okay, so means that here the sign here show that positive times whatever input and that negative here times whatever output. Okay, so if you have both positive, so your output here be x plus y. Okay, so this is how we do summation. So we can use either three symbols. Okay, so some textbook use the first one, some use the second or the third. So some they mix. Okay, so and then this is the block diagram for integrator. Okay, so if your input is at T, so the operation in here is integration. Okay, so this system we call it integrator. Okay, so the output will be the integration of this xt. Okay. Okay, so this is feedback systems. Okay, so in the feedback system, the response or the output here is feedback. So here, if you have this block diagram, see the output. So you have the system input here. So this is summing junction, and then the input is X. Okay, so the X go to the summation junction. Okay, so goes into the system G, right? So the output be YT, and then the output will be feedback. Okay, feedback through H, and then go to the summing junctions. Okay, so is feedback. So in this case, the response or output of the system is feedback and combined with the excitation to optimize the response in some desired sense. Okay, so these are example of the feedback systems you can have, and you can read this. Okay, that is feedback systems. Okay. So system modeling. So you know that you learned before this signal, and then we have here system. So system modelings, okay, so means by here describe the system mathematically or graphically or logically. Okay, so you have system, all right, the input is xt, the output is yt. So we can have system modeling. So the system modeling is used to describe, so the system modeling is used to describe the system together with the input and output. Before this, you look at the signal. It's the signal expression in terms of mathematical expression. Xt equals to sine t, xt equals to cos t, xt equals to ramp function, xt equals to unit steps. Okay. So now if we have systems, so how do we relate this system and the signal? So we use system modeling. So in the system modeling, so we can use modeling can be used to describe to show association between input, output, and the systems. Okay. For example, here in the electronic system, we do have RC low pass filter. So RC means resistor capacitor. You learn this in circuit theory. You have RC circuit, you have RLC circuit, you have RL circuits. Okay, that's systems. Okay, so how the input signal that is V together with the resistor capacitor, and then the output, how this connect with each other, how this signal and the system associate with each other. Okay, so we also have the other uh, system, like here you do have analog digital converter, you have a amplifier. Okay. Okay, this way. Okay, so so RC filter circuit is example of a system. Okay, so it consists of two components, that is resistor and capacitor. So that the resistor and the capacitor form the systems. Okay, So you have the input voltage and then you see the output voltage. Okay. So other component in the electronic system, you can have inductor, you can have op-amp. Okay. So a lot more. Okay. Okay. So to do engineering design, we must be able to accurately predict the quantitative behavior of a circuit or other system. So this requires mathematical model. Okay. So for example here, so we said that RC low pass filter is a simple electrical systems. Okay. So the input voltage is V in and the output voltage is V out. So you know signal. So the output voltage, this is signal, your signal or input signal, So V out is the signal for the RC circuit, output signal. Okay, so here we do have so you have the R and C. The R is the resistor, C is the capacitor. So the input is V in, V out is output. So V in and V out is signals. Okay, RC and the wire that form the system. Okay, so we can write as a simple block diagrams next to it. You can see the block diagram. Okay, sorry guys, just wait. Okay, let me use this PowerPoint only. See my PowerPoint here?
Yes, doctor.
Yes, doctor.
Yes, doctor.
Okay, so you see here, so the RC and the wire or the circuit there is in the block or in the systems. Okay, so you can draw the circuit as a block diagram, a simple block diagram where you have the input voltage as input signal and output voltage as output signals. Okay, so it can be viewed as single input, single output systems. Okay, so this is for RC low pass filter. Okay, you can also have RLC, RC. So in this case, your RC is in series. You can have RC in parallel, RL in parallel, RLC in parallel, RLC in series. So you can have that. And then what is the input? So the input is is current or voltage. Okay. So that is how we model the circuit as systems. Okay. So before this, we just last 2 weeks we just discussed on the input signal, output signal. So when we use model, we can show relation between system, the circuit, and the input signals. Okay. So for example, here the for the RC low pass filter, you have here input voltage. So the input voltage is the unit steps AUT. So if you have here V in is AUT, so AUT, you know UT is unit steps, right? So UT is unit steps, right? And then its response or output is A1 times 1 minus exponent negative T over RCUT. So this is the output signals, okay? So from here we know that if the excitation is double, okay? So the response will be double, and we use differential equation to describe this continuous time signal T. Okay, so differential equation is the best way or is the easiest way to describe the continuous time system, continuous time system and systems. Okay, so we can use differential equation to describe RC circuit. So for example here, so you have this in circuit theory. So where R you have voltage across R is Ri. Okay. So let me try connect this again. Okay. Alright. Okay, it's not working. This okay, it's okay. So here you have the R. So the voltage across R is Ri. So if you have current flowing through this resistor, so Ri is the voltage, and then I is V over R. And then for the capacitor, so this is just to recall, okay? So the current for the capacitor is C dV dt, okay? And then for the voltage is, you need to do the integration, right, to get the voltage, okay? And then the last, the third component is the inductor. So for inductor, the voltage induced in the inductor is L dt, and then the current can be obtained from these integrations also. I think you have seen this in the circuit theory. Okay, so if we have the RC circuit, okay, we can describe this using differential equation. Okay. Okay, so the differential equation is the best, easiest way to describe a system, and one is because we can easily find the input and output, okay, V and V out. So we can solve that differential equation. So that's why we use the differential equation. Okay, so for example here, so to show or to describe this, so to describe this circuit using differential equation, so you have to use this Kirchhoff voltage law. Okay, so you have the input voltage, so you know that V in equals to VR plus VC, because you know this is in series, right? R and C is in series. So the voltage, input voltage equals to the input voltage equals to the voltage across R plus voltage capacitor by the capacitor. So you know this is Kirchhoff voltage law, right? Okay, so and then from this whatever given here, so you know V across resistor is RIT, okay, because you know the current flowing in the circuit is IT, and the voltage across the capacitor is given by V out, okay, here V out, okay. So you have this this one, and then you have this one, right? Okay, so and then you know that the current in the circuit, the current flowing through R is also current flowing through the capacitor, and the current flowing through capacitor is C dV dt. So you have this I, right? So substitute this C dV dt into the equation. So you have RC dV out dt plus V out. So see, you have the differential equation. So this differential equation is used to describe the system. You see, you have the input, and then you have the output, and then you have the R and C in this equation. So this is why we use the differential equation to describe the system. So we want to see the relationship or the association between this input voltage or input signal, output signal, and the system, that is RC. Okay. So this is for RC. So you can have for RLC, okay, the RLC circuit, RL circuit, either the signal, the circuit is parallel series. Okay, so you go and check for that. Okay. Okay, so this is example. Okay, so we can use differential equation to describe systems. Okay, so if you look at this differential equation, so see that this is a system showing or described system because we have input, output together with the component in the system, R and C. Okay, this is not signal. Okay. Okay, and then we look at the properties. Okay, so for system, we only discuss on the properties. Okay, first the properties is homogeneity or homogeneous. So if you have this system, okay, so if you have a system and the input is xt and the output is yt, okay, the same system, if you have this multiplier, okay, this okay, so xt times k, so you have kxt, so the output is kyt. So we say that the system is homogeneous. Okay, so this system is homogeneous. If you have xt times kt, but you got output here, not k, got output in bt, byt, so this is homogeneous. So whatever you have in input should follow at output here. Okay, so if you have kxt as input, you will have kyt. Okay, if you have bxt at input, you will have byt. Okay, so that is homogeneous systems. If other than that, if you have kxt as input and come from the system is not k, zyt, that is not homogeneous systems. Okay. Okay, so this is again, okay, and then time variance or time invariance. Okay, so if a system is initially in its zero state and an arbitrary excitation cause a response yt and delaying the excitation by t minus t naught simply delays the response. Okay, so that is means by time variance. So if you have this is the system, right? So if you do, if you have time delay on the signal before it goes into the system, that is minus t naught right here. So the output also follows the same, minus t naught. Okay, so we said that the system is time invariant. Okay, if you have input here, delay by t naught, okay, so you have xt minus t naught, so here, but your output here only yt, sorry, So YT. So this is not time invariant because why? So the output should follow input. So if there is delay by T naught, so output should have also delay by T naught. Okay. If input have advanced, okay, instead of okay, let's say instead of I want this pen. Okay, instead of T minus T naught, let's say you have advanced. So if you have advanced T plus T naught, okay, so the output also have T plus T naught. So whatever happen in the input should follows at the output. So that is time invariance, okay. And then additivity, okay. So for additivity, so here if you have the system, the input is X1, so the output is Y1. If you have the same system, the input is X2T, so your output should be Y2T. It follows. Okay, so when we do the addition at the for the signal before it goes into the system, X1T plus X2T. So the signal goes into the system, the output should be Y1T plus Y2T. So we said that the system is additive, or the system has this additivity property. Okay, if you have this as the input, but your output only have Y1T, no Y2, no this part, so that is not additive. Okay, so to be additive, so you have X1T plus X2T, so output also Y1T plus Y2T, so that is additive. Okay, so if we combine here homogeneous and additive, we call it a linear system. And if the system has linear and time invariant properties, we call it linear time invariant system. So linear combination, both homogeneous and additive, so we call it linear system. So if you want to test whether the system is linear, so you have to test for homogeneous and additive. And then if you want to have or to test for linear time invariant, so you have to add another properties that is time invariant. Okay, this is stability. Okay, so any bounded input, the output either remain constant or decrease with time. We call it stable systems. Okay, so you see that here the input here is constants, right? Constants. Okay, with amplitude 1 is the unit steps. Okay, so if it go into this system, okay, so the output is, see, it increase a bit and then it decrease with time, so we call it as a stable system. Okay, or you have the same constant, or this input become this output decrease with time. Okay, so this is a stable system. But if the output, let's say, is this output going up nowhere, so this is not stable system. So it's either remain constant, the output either remain constant or decrease with time only. If the output increase with time, the system is not stable. Okay, right. Okay, this is incremental linearly. Okay, so I don't want to discuss much on this. Okay, I want to say this causality. Okay, so we said that a system is causal system if output depend on the present and past input only and not the future inputs. Okay, so for example here, okay, let's say here, so this example of the 1, 2, 3 is an example of causal system. See, you have yt is the output and xt is the input. So it shows the relationship between output and input. So this is a system. So you need to determine whether the system is causal or not. So looking at time there. So for the first one, the output at time t here. So you have t. So the output at time t equals to the input at time t and input at the past t minus 2. So it depends on the present input and past input. So this is causal. Okay. So same goes to the second. So yt input at time t depends on the output at time t equals or depends on the input at t minus 1 and the minus 1 minus input t minus 3. So t minus 1, t minus 3 show the past input. Okay. So same goes to the third example here. The output at t at the present time now depends on the past input t minus 5 times and then times 7 here. Okay. So that is causal. Okay. So here we have anti-causal. Okay, where the output of the system depends on the future. So future we can write as t plus 5, t plus 1, t plus 2. Okay, so t plus 3. So that plus show is future input values. So here output yt at the present time, at time now, depends on the input at future time, that is t plus 5. So this is, we call it anti-causal system. Okay, it in contrast or opposite to the causal systems. Okay. Another type of properties that is non-causal. So non-causal is the mix between system response depends on past, present, and futures. So means that you have xt plus 1, xt minus 1, xt. It present on present, past, and future input. Okay. Okay, non-causal system contain future samples. Non-causal system is practically not realizable. Okay, so in practical cases, so in real life, we only do have a causal system. Okay, so that system that depends on the input at the present time or at the past time, not future. Okay. So, and then system with memory. Okay, so if a system response at any arbitrary time depends only on the excitation at the same time, that is present time, and on the excitation or response at any other time is called static system and is said to have no memory or memoryless. So we can have it, or we write it as memoryless. Okay, no memory or memoryless. Okay, but system with memory, we call it memory system or dynamic system. So integrator has memory because when you do integration, you have to plus C, right? So the initial condition, what is the initial condition before you do that? Okay, so you normally integrator. Okay, so that the properties for systems, continuous time systems. Okay, so we do have homogeneous, we do have time invariant, additivity, okay, and we do have stability, causality, and memory. Okay, we do have more, but this is the most important thing. Okay, so we just choose few. Okay. Okay, so same goes for here. Discrete time systems, okay. But discrete time system, okay. If for continuous time system, we have differential equation. But for discrete time system, we do have difference equation, okay. Two different things, differential equation and difference equation. So this difference equation is used to describe discrete time systems. Okay, so how do the difference equation looks like? Okay, example here. So here, so this is a difference equation. Okay, so n-1, n-2. Okay, so we don't have DDT, the differentiation, right? Okay, so the block diagram. So of course, because this is a discrete time system, so we do have discrete signal xn. So this box shows a delay. Okay, so when it goes a signal at n goes into that box, so you have delay by 1 units. Okay. Okay, so difference equation, not differential. So this is example of difference equation. So this is how we see in words. Okay, so the signal value at any time n, that is yn, or the output signal at any time n, is 1.97 times the signal value at the previous time, n-1, minus the signal value at the time before that is 9-2. Okay. So this difference equation used to describe discrete time system. Okay. So the discrete time system also can be described using this block diagram. Okay. So if you have this different equation, so you can draw this as a block diagram. So see here, the output is yn, go into one delay. You have, when it come out from this box, you have yn-1. Okay, so times this constant 1.97. So you have the summing junction here. So it goes back here, right? So and then if yn-1 go to the second delay box, so it become yn-2. So if you sum the first signal and the second signal here, you have this 1.997 yn-1 minus yn-2. All right. Okay. And this one you can just have a look on this, but you can plot this by when you have this initial condition. Okay. So go and think how you got this. Okay. So when this y0 equals to 1, so n is 0. So here n is 0. So when n is 0, the amplitude is 1. So the amplitude is 1. That's why here the amplitude is 1. Okay. So and then you can use this equation to plot others. Okay. Okay, for discrete time system, the properties are the same with the continuous time system. We do have homogeneous, we do have additive, and then we do have homogeneous and additive is linear, and then we have time invariant, etc. Memory, memoryless, we have causal, same. Exactly the same with system properties for continuous time. So that's why here we can just use that previous slide, okay, to look at the properties. Exactly the same, okay, for the system properties. So both continuous time system and discrete time system has the same properties. Okay. Okay. So now I want to do the example.